it's still, I mean, this analogy for me, this building this giant brain on top of this perceptive input that comes from the big universe. That amazes me.
Yeah, it is amazing. I mean, I think the coming decade, the coming 2 decades or something, will be the combination of. So it's not just LSST. There will be a range of new observatories with these different messengers that I hope will be constructed, and it's kind of the combination of these with the new AI techniques that, in principle, I mean, it will allow us to discover just completely new facets of the universe that we had no idea existed before. So this is this scientific kind of potential here is extremely exciting. It's then the question how we can go there in a way that doesn't drive everyone insane that's trying to do it.
My name is Balázs Kegel, and this is the iScientist podcast, where we explore artificial intelligence, the body, and the soul. This is my great pleasure today to host Jakob Nordin. Jakob is an astrophysicist in Humboldt University in Berlin, Germany, and he's a member of the LSST collaboration, which will be the main topic of today's conversation. So how are you, Jakob, today?
I'm good. Thank you. Thank you for inviting me. How are you?
I'm great. So let me just introduce a little bit why we are here. So we met a month ago. I gave a talk to astrophysicists about something completely different, but the audience was very receptive to my presentation about the future of engineering. And after we had like a 2-hour conversation in the reception, and we started to talk about what you do, which is LSST. It's an astrophysics experiment. It's an observatory that's being built, so we will talk about this. So what is fascinating about this, so I knew this experiment from the time when I worked with physicists in Sackler University, where the presentation was, and I understood already that this is going to be quite different from what we've been doing in astronomy, not only in the sense of its size and technological advance on the hardware, but also the informational structure and the computational structure that we are building on top of this observatory to deal with the enormous amount of data that it will collect, which is something that's pretty new in astronomy. So this is why I wanted to talk to you, to understand a little bit who you are, what you do, the experiment, talk a little bit about the actual hardware, so the telescope that we are building, and the informational complexity and the structure which you are participating in, that we are building for dealing with this. So my first question would be like, who you are you an astronomer or an astrophysicist, and what is the difference, and how did you become one, and what did attract you to this beautiful domain?
It seems unfair to already start with a question that I can't answer. Typically, so what's an astronomer, what's an astrophysicist, what a physicist? That's a very it's a very fluid distinction. So I think I typically say that I'm an observational astrophysicist. You could also say that I'm a physicist working with astronomical data. That's
So this means that as a physicist you are interested in the physics, but you are interested in the physics that explain astronomy.
Yeah, at least originally my goal was to understand the physics. So the physics, the natural laws that govern our universe in principle. And then we use observations of the astronomy to try to better nail down those laws. Basically, the Earth where we live is a very small place, and there are many tests we cannot do here because it's too cold, it's too small, and the only way to attack those even larger questions is to use the whole universe as a lab. So that was my original starting point. As I think we'll get to these days, what I'm actually doing is try to design systems that can actually process all of this data or understand all of this data that we're getting from observatories that look out into the universe.
It's quite fascinating to me. My father was an amateur astronomer, and he's a mechanical engineer who built telescopes in his spare time. For an amateur astronomer, they were pretty nice. So when I was a child, we could watch the moons of Jupiter and the Saturn's ring from the porch, and the neighborhood gathered around this. It was almost like a ritual of looking up in the sky, like Galileo did. And so he actually dreamt about becoming an astronomer. Are there any astronomers per se remaining in science, or we are all astrophysicists who work with astrophysics?
I mean, that's again where I think the distinction becomes subjective. You can, I think most people working or scientists working with astronomical data are still astronomers in the sense that they are trying to map out what happens in the universe, what sort of objects exist there, how do they work, where do they come from. But then, of course, it's a sliding scale that all of that is driven by physical processes. So as you pursue those questions, eventually you come into these questions. How do these objects actually work?
I see.
I think in the end, it's a pretty random definition that probably is decided by what course you happen to take first in university. So in practice, it's a distinction that doesn't matter too much.
I see. So it's basically you have a sort of cataloging thing, like you look at the individual objects and try to categorize them and understand what they are, and then there's the physics behind, which goes deeper into what are the laws that govern all this, right? So it's
that's like one way to make a distinction. Again, in a practical case, it's typically fluid, but yes,
okay.
I mean, you can probably make a distinction, but that some science groups are happy cataloging every kind of variable event that can happen, and other science groups are only interested in determining the few parameters that govern the universe at its largest scales. And then there's any sort of kind of intermediate research interest.
I see. So we'll get there, because I'm very much interested in the sociology of all this. Like we had Vava Gligorov on this show, who explained us how particle physics works and how the collective actually acts as a filter to make sure that what we publish are really the truth, and that there is a convergence because we have to build bigger and bigger instruments. So a lot of people with different interests have to converge to what we actually build. So there's also an interesting sociological process of how to do this. So we get in there, and I want to smoothly go into the topic of LSST, but give us perhaps a historical view of what are the type of instruments we've been building, how we arrived to this this huge telescope that we are building there, and what are the kind of scientific questions that we want to answer with these.
Yeah, maybe if I take a little bit half a step back. In principle, if we think about astronomical observatories, we can kind of arrange them in a few different dimensions. First of all, they can observe with different messenger, so looking out basically for different particles. So this is where we would have photons or neutrinos or gravitational waves or cosmic rays and so on. And then we can think about the energy scale. So how energetic are the particles that we're looking at? So that would form another dimension. And then a third dimension would be, so what field of view are we looking at? Are we looking at the small patch of sky, or are we trying to monitor everything? And then we can add a fourth dimension, so a time dimension. So are we trying to create a map, a fixed static map of say, all the galaxies that are out there? Or are we trying to have a dynamic map that maps every few days or a few seconds to look at everything that's varying in the sky? So kind of we can put in different observatories in these dimensions. And basically gradually, as we have learned to build better and better telescopes, observatories, we've been, of course, driving into the extreme in all of these categories, all of these edges. So what started at LSST? First, we should define it. Now it's the Vera Rubin Observatory. Vera Rubin, very influential astronomer, who kind of cemented the idea that dark matter must exist out there. So it's very suitably named after her. And then the actual survey that's going to carry it out is now called the LSST survey. And it's been built now in Chile. It will be completed next year, I hope. And in terms of where we land in this dimensional space, it will actually be pretty good on a lot of different things. So it has quite a large field of view. It observes basically across the wavelength spectrum for photons, which is observable from the ground. So basically optical wavelengths, in principle, what we can see with our eyes. And it will have some sort of cadence. So every few days, it will return to the same patch in the sky so that we can detect new variable sources. And kind of adding all of these together makes it into a unique observatory that will both produce the most detailed map over all of the southern sky at the same time as producing lots of information of these transient events, these variable objects that exist out in the universe. So it's going to, we can't really see it as one experiment, because it's a kind of a peak of a lot of technological developments that will allow us to do many different things. So both have a very detailed view of the full sky, as well as look for very distant or faint transient events.
Okay, just to give an idea to the listeners, we get a lot of images on the internet from the Hubble telescope, and more recently from the James Webb, which are photos taken by a telescope on a satellite, right? So, as I understand, the trade-off is that we cannot send a huge mirror up to this to the space, because it would be too complicated technologically. But the advantage there that there's no atmosphere, so you can go much deeper, but the field of view is much smaller, right? So that's more like a classical telescope, because as I understood, it used to be like you had this telescope built by some agencies, and then the astronomers and the astrophysicists signed up for telescope time and asked the telescope to direct themselves to a certain patch of the sky, and then they took observations, and whoever asked for it analyzed the data. So the satellite-based telescopes work more like that, right? Because they have to choose where to look, whereas what LSST will be is a survey, a pre-scheduled sweep of all the sky. So nobody will have to actually decide where to look, except for maybe 10% of the time. because it will automatically sweep the sky, and then the data will be just somewhere. We'll talk about it, of course, and it will be analyzed. But you will, for example, not ask LSST to look at a certain patch, right?
No, that's and it's kind of typically with these wide field telescope, to look at a specific individual point in the sky is usually a waste of your beautiful machine, which is really designed to look at large volumes. So it's really, these are really complementary facilities where the space telescope, as you say, they're outside the atmosphere. So both the photons are not absorbed or perturbed in the atmosphere. So you can really observe individual systems, very distant objects, or very or observe nearby objects with extremely high resolution to really figure out every little detail of what happens there. So they are magnificent tools for that purpose. So they will really complement each other, where LSST will provide this wide, deep volumetric study of everything that happens, while HST and Webb can then do detailed examinations of single points in this huge space.
Okay, so let's talk a little about numbers, because I just went to check it out, and it's like mind-boggling what's going to happen here. I don't know how. So I would be really interested in the actual hardware. So what is the size of the telescope? How is it built? Who is building it? Why does it take so much time to make a mirror, etc.? So these are all fascinating questions for me. So anything that you can tell us from this angle?
So a lot of the numbers I wouldn't know by heart. It is in a lot of ways it uses. I mean, it's hard to build a large telescope for many different reasons. One is just that an optical telescope contains mirror, which becomes very heavy if you try to build a large dish, which makes it, and of course you need to keep it in a very specific shape to focus all the photons into a single spot. So that produces kind of a natural limit for how large you can make these telescopes. So one of the evolutions we're seeing now is that it's actually split up into smaller segments, and each of these segments are specifically then controlled while you're observing to keep the dish in its perfect shape. So these are kind of one set of technological evolutions. The other step has to do with the other kind of great evolution has to do with the cameras we're dealing with. Right, the limiting factor 20 or 30 years ago used to be that the CCDs were tiny and not very sensitive. And now, if you look at the LSST camera or the Vera Rubin camera, it's a huge thing where actually the physical sensor size, again, I don't remember the numbers, but we now have the technology to actually build large wafers that are extremely sensitive to optical photons. So these are kind of technological developments that allowed to build a large telescope that can serve this wide field of view in one shot, and basically in 30 seconds or so go deeper than we've ever gone before in a particular direction of the sky.
Okay, so it's basically, it will take a photo every 15 seconds or 30?
It's still being optimized, but probably 15 seconds and then another one, so you can reject things like cosmic rays between them. So we'll take two quick observations, and then we'll move to a slightly new patch.
Yeah, because cosmic rays attack the CCD directly, right?
Yes.
And they will make little pixels, and if you take two photos, then you can filter them out. It's ingenious.
Exactly. That's the easiest way to get rid of them.
So one of the things that is mind-boggling for me is how you deal with the atmosphere, because 15 seconds is long enough that if you look at the sky by naked eye, you see it's vibrating. It's vibrating not because the sky, the original object is changing luminosity or direction, but because the air changes the turbulences change the directions of the photons. So how do we deal with this? Because 15 seconds is too long for, or maybe This is why it's 15 seconds, so you can cancel it
The
out.
first thing we do is that we go to mountain in a desert. I mean, there you have much less atmosphere, and the atmosphere is much more stable. So to a certain degree, that reduces this turbulence, but it will not remove it perfectly. In 15 seconds, every star will experience this little jingle, and you will basically integrate over that so that you see an average over that position, which is unfortunate, but again, that's the distinction compared with space telescopes, because there you get rid of this effect completely. There are other instruments where you can experiment with lucky imaging. So you take really, really short exposures and then you try to combine them in a way to get rid of this jiggle. But then you get a lot of other inefficiencies. So the primary way to do it is to go to really good site and then live with it. That's the residual seeing that we experience.
Yes. So I was in a Pierre Roger collaboration, and it's not far from Chile, actually, on the other side of the Andes. And I'm just, it's an interesting thing that because of these sort of technical considerations, these observatories are getting built in really exotic sites, and you get to go there and see the desert or the plateau of Malargüe for Roger.
Before everything became virtual, it used to be one of the nice aspects of doing astronomy a few times a year. And also before, you didn't have to avoid flying. You could go to Chile or Hawaii because you actually had to go up to these remote sites and you had to be there in person.
Yeah, the Canary Island, I've seen the telescope. It's a beautiful site, yeah. Okay, so I do have some numbers and I would like you to explain what those are. So first of all, there will be 7 trillion detections.
Yep.
What is a detection?
A detection is a variable object that's seen when you take one of those 30-second exposure. I assume already we take 2 15-second exposures, we get rid of all the noise, and then we look for new astronomical sources in this image. And typically we do that by subtracting a reference image, so an image that we made that contains no variable light. And then we subtract it, and we see if there's some residual light source in this image. And typically there will be. And that is then called a detection.
Okay, so that's only the variable objects, variable luminosity objects, the detection.
Yes.
I see.
And of course, a constantly varying object might be detected many times.
I see. So okay. So it's not per object, but per change.
Yeah.
And so give me an idea about what are the broad categories of changing objects.
The first category would be just noise. We talked about cosmics, but there are plenty of other noise that could be coming from the instrument, from the way we do the subtractions, or from the atmosphere, from surrounding instruments, whatever. So these are obviously boring events for any users. So hopefully we can get rid of those. Then we get to kind of the astronomical categories, which we can split them up in a few different ways. But we can start with solar system objects. So that would be planets, asteroids that exist in any size. Of course, as you go fainter, we will discover many, many more objects in our solar system. Then if we go slightly further out, we get to the Milky Way. If you look closely enough at stars, most of them will be variable one way or another. They are not static in their lifetime, but a lot of them experience some sort of pulsation or vibration. This could be, for some types, this could be very violent. For others, it could be almost non-existent.
Does the sun vary like that?
Yes, I mean it does. We have all the sunstorm and activities and so on. It's not on a very high magnitude. I think viewed from a large distance, our sun is now in a relatively stationary state, but a lot of other stars vary very repeatedly on everything from very short to very long timescales. And that's, of course, a key to understanding the physics that actually drives the star. Is it related to some gravity effect where it's close to collapsing? Is it because there's a wind, material being thrown out? Is it because we actually have a system of many stars that are orbiting each other? All of these cases will happen, and you can try to disentangle them by looking at this variability. So then we go further out from the Milky Way to extragalactic phenomena. And there we find two broad categories, at least the way I see it from an informational point of view. The first has to do with basically black holes doing stuff in the course of galaxies. So, and that's what we call AGN or quasars and so on, depending on their state and how we're looking at them. So AGNs are, of course, black holes are, of course, very powerful phenomena, and we might think of them as dark, but in this process, typically in large galaxies, we have a black hole in the middle, and the process where this is accreting material, some of it is added to the black hole eventually, and this we don't see, but a lot of it is being thrown out in very energetic processes, and this we see as variability. And then we have the final category, and that's where I'm mainly focusing my interest, and that has to do with explosive extragalactic transients. So these are typically supernovae. So stars at their end of their life that end in a very violent explosion. That is short term. It might last from a few days to a few months on that time scale.
Okay. So there will be 7 trillion detections. This is for the lifetime?
Yeah, that's for the 10 years of the nominal duration.
So there are 37 billion objects. I suppose those are the ones that don't change. Like half of them, about half of them are stars, half of them are galaxies.
Yeah, yes. So these are things that have been discovered in these maps that will be created. Most of them will probably be detected as variable at least once to be registered into this, but they will be of any different category.
Okay, so these are just the variables. Okay, I see. And the next number is the nightly alert rate, which is just amazing. So there will be 10 million alerts every night. Where I guess alert is something that's there this night, which wasn't there 4 days ago.
Yeah, or whenever this field was looked at before, and this will vary. So we do this subtraction, and LSST will be shunting along the sky with the sensitive detection. Every 30th second, we will do the subtraction, and then in every image, wherever we're looking, whenever we're looking, everywhere there are variable events. And for each of those, there will be an alert distributed saying, hey, something is happening in this position. And that's then...
Now, 10 million alerts is too many for astrophysicists to actually look at them, right?
They are, definitely.
Why? So first question is why do we alert? Why don't we just store it and analyze later?
That's a good question. And for some science directions, that's perfectly fine for some science projects. But for a lot of applications, for me or just for general studies, you can't do that because you need to react to the alert as it's coming to follow this transient, if it is a transient, up with other instruments. Because here we come back to this complementarity between, say, LSST and Webb or other ground-based telescopes, in that when you look at the full energy range that a transient could exhibit, so that any physical variability that could be there, LSST is very sensitive. It looks over this wide sky, but it's actually only sampling a very narrow energy range in this whole band. So to actually understand what physical process is going on, we need to detect it and then get on this particular objects with other instruments. It could be at other wavelengths. It could be enough to look whether anything else was seen there. It could be getting a spectrum. Because since they are transient events, if we don't look during this week or month, then it will be gone. So there will be no use going back and look for it later.
I see. So we want to catch this, for example, something is exploding, we want to catch it in the beginning so we can measure it with other instruments. And this is also something that fascinated me, that we have this what's called multi-messenger astrophysics or multi-messenger observatory, where it's basically a network of these observatories that put into the same information system so they can catch each other's alerts, and those where you need to make a decision to focus somewhere can be focused onto the interesting events. So I know, maybe you know, probably you know more of this, but we have gravitational wave experiments like LIGO and Virgo. We have Auger and telescope array, which look at high energy cosmic rays. We have, of course, the photons, gamma ray, radio, so all kind of different communities who build different telescopes for different reasons, but for this particular reason, to catch the fast changing objects, you guys collaborate. So it seems to me almost like, if I look at the Earth as an ecosystem, these are the different sensors, eye, ear, hand, and there is a sort of attention mechanism built on top of this. These are this alert where you get some light into your eye here, you turn your head there, you try to catch it, or you try to go away if you're afraid. So it's almost like we are building like this beast, like this living beast, where each little piece is sort of like, we'll get into the AI part, but it's becoming intelligent, and then the whole thing is like a collaborative detection mechanism of interesting things out there in the universe, further and further away, and in time and space. So it's amazing. So let's talk about this infrastructure a little bit. So first of all, what is this multi-messenger thing? How are these alerts handled, and what is the infrastructure you're building, not only in LSST but in the other observatories?
So the picture you view of this multi-sensor, I wouldn't call it a beast, but I mean, there are other beasts. I don't think that's a beast. I think that's kind of a critical way to actually understand what's happening. I think it very much is similar to our different senses, that when you look at these transients, you learn very different things as you observe it with different sensors. I think the gravitational waves, that's of course the prime examples. We now have these amazing sensitive detectors that can actually feel when gravitational waves are propagating through the Earth. I mean, that in itself is mind-boggling. And through that, we can, for example, study emerging black holes. For those we won't see much. But there are other events that give rise to gravitational waves, like merging neutron stars. So these are also extremely interesting physical objects that will give rise to a gravitational wave, but also signatures in, for example, optical wavelengths and in radio wavelengths. And there you definitely get different sorts of information, like from the gravitational wave, you can tell that something happened and how massive these neutron stars were, but you don't actually know where this happened. Your localization is not very good. And this is where, for example, optical telescopes are actually really good. You can then scan through an area and find the correct locations, and then try to see, do I find a new transient here that could match the signal we got from LIGO Virgo? So how does this work? In some sense, it's pretty crude now, but different observatories, when they get those detections, they send out notices. Partially it's still by email, partially as Kafka alert streams, but you can listen to these, and then you get you get the announcement, and then if you have control of a telescope, you can decide to observe this or not. So this is a lot what these multi-messenger groups are doing, in the sense they listen to different alert streams coming, and then they make decisions on what to do with them. We are not quite at the stage that I think you described yet, where this is an automatic process. It's still very much a field that's emerging, and when there are still fairly isolated communities that are discussing every alert and thinking about what information do I make public, what do I tell whom, and what events do I trigger on, what do I not? So there's still a lot of kind of developing sociology there.
Yeah, it's fascinating. So I didn't mean that it's already all AI-fied. I'm just saying that from far it looks like, I mean, we are part of the network, like the human attention is part of this attention, but from far away it does look like and by beast I didn't mean any negative. I just mean it's almost like a living organism that has sensors which are much more sensitive than ours. We are part of them, and we are building the attention mechanism, which is very, very important, because like 10 million alerts a night, you cannot assign people to each of them. And so you are forced, maybe some others have less alerts per night, so they can still have the astronomer or the astrophysicist on shift, which is also an interesting concept. I remember in Auger, we have shifts. They do have these in particle physics experiments too, like people who go there and they have to monitor the things 24/24. And I guess those people could be involved in the decision of directing some observatory to some spot on the sky, but not when you have 10 million alerts a night. So here you must automate some of the attention mechanism, which also means that, as you told me when we talked first time, that we will actually throw away a lot of things without actually humanly looking at them. We have to, because there is not enough attentional space in our brains. So how does that work, and what's the role of AI in all this?
If we wait a little bit with the AI part,
okay.
So the question about how to process these data, as you say, it has to be automated. It's the only way to do it, and in practice, what we are trying to do, what my group is trying to do, is to build infrastructures that are fast enough to process these data streams, but where scientists can still define scientific workflows that actually highlight, so these are the kind of events that I would be interested in, and then they are applied to this alert stream, and they then do this automatic filtering, such that ideally only the really interesting events come out in the end. So that's kind of, as you say, this process needs to be automated. We are right in the middle of this process, and for some kinds of projects, this is going very well, for others not. There's, of course, always the brute force method of throwing away 99% of the data, or 99.9, look at the remaining, and you can still do science, but that's the...
So this is a beautiful concept, and in your presentation at the same workshop where we talked, you said that there is a sociological paradigm change here, because most of the time astrophysicists and astronomers, the way they were just looking at the sky and get inspired by the data they saw. Whereas here you have to invert the process. You have to first define what you're interested in, almost like a hypothesis, like in the scientific method, you have to code it into an attention mechanism that will look at the actual alerts and output a positive or negative decision, or whether this is what this falls in the category that you defined as a workflow, like a computational decision mechanism. And then you get the data and then you analyze it, and it's what you gain is, of course, that you will have an automatic workflow that will give you the data that you analyze, and what you lose is the insight, maybe, or
Yeah,
the getting
and
inspired by unknown things that you see.
and at least maybe the illusion of that you follow some sort of scientific principle. I don't know if this idea that this method ever did, but yeah, it is really paradigm shift. Astronomy is, of course, an ancient science since thousands of years, and you can summarize it as that men, because typically it has been men, has been looking into the sky, and they've been very smart, and they have seen something, and they have then written down an idea of what could explain this behavior. And it's been very successful. And it's to our day how most observational astronomy is being done. And it's been very successful, and it has allowed for a lot of diversity. So compared to a lot of other science direction, astronomy has managed to be very creative by being a very flat organization. There's been many small groups that have looked for or looked at specific kind of phenomena, like what they think is interesting, and then they have seen something and they have explained it. And it has created this amazing breadth of different things that are being investigated, because there are frankly so many different things in the universe. But as you say, this idea of being reactive to data just does not work if you want to take these data flows seriously. And it's not these 10 million alerts per night. That's actually the easy part, going through those. The hard part is when you consider that for each of these 10 million alerts, I would then have 20 different actions I could do. I could trigger that telescope, I could do nothing, I could do this, I could do that, I could record it, I could send an alert. So if you consider that space of everything that could be done, it becomes huge. And then, of course, all of those decisions could trigger another decision. So if you followed it with a transient with one telescope, maybe you detected it and triggered another telescope, or maybe you didn't. So suddenly you have this huge tree of possibilities. And I think in principle, those principles existed before, but we didn't know about them. So we couldn't take them into consideration. Now, in principle, we can, but how do we do that? And there then, the only way is to be proactive instead, to revert this process. And this was what I mentioned, to first, without having seen what's out there, write down an hypothesis, write down a pipeline or construct a model that would be sensitive to find some specific kind of thing, and then throw that out into the data and see what happens. So it is a different way of trying to look at this variable objects.
It reminds me slightly how living perception works, cognitive science. Of course, the goals of a living organism are pretty clear. First of all, we want to survive. So all the perception and attention mechanism is highly tuned to things that can happen, that can threaten us. We also have goals that, like, we want to eat, drink, etc. So that's how sort of like consciousness and perception solves it. But one of the attributes of perception, which it comes up a lot in AI because of the hallucinations that we see in the large language models, is that we hallucinate a lot, in the sense that we build an internal model of the world, and we project it onto the world almost like an augmented reality system. And a lot of times we don't really see what's coming in because we see what we project. And that can, of course, go wrong when it's only projection and you can become psychotic. But there is a delicate balance between this projection and it's, some say it's like 80% of the perception system is doing the projection and 20% is what's coming in. And then there is this very similar like alert and attention mechanism that looks at prediction errors. Because if my prediction is what's happening, I don't really need to pay attention. And it's at every level of your organism, cellular or high level. But if something happens that your internal sort of generative model doesn't explain, then you should probably pay attention to this. So I'm wondering if there is something like this and this system is basically tuned for dealing with unknown unknowns, things that can happen that I don't have a model yet. Because a lot of those things happen when you are in an uncertain situation and you live. And that solves this problem a little bit, that those things that we would lose if we only had like fixed pipelines looking at certain categories of events, we would lose those that don't fit into those categories, that don't fit into any hypothesis, because the hypothesis was inspired by the novelty. So I'm not sure. Do you have any idea or anything going on in this experiment on how to deal with those?
I mean, that is the question of the unknown unknowns, that's very much relevant, and it's very in some circles it's very much discussed consciously, that this is the official topic, or kind of unconsciously. I think that's for a lot of the I wouldn't call it old school groups, but in this reactive way, this is actually one of their main criticism of this new way, that whatever pipeline I can cook up, I don't trust it to recognize when something's new and different, while I trust my intuition and my knowledge that if I would see such an event, I would realize this is something unique and new that's challenging. So in a lot of ways, that's behind that's behind the reluctance to shift into this other proactive way to deal with this problem. There is kind of from the other side of the community, we could call that the AI community. The imagined solution has been to build some sort of anomaly detection machine learning models that would also parse through the data. I don't know if I'm somewhere in the middle, but I've never actually seen such a model that works on real data, that produces based on astronomical data that we have, because at least so far, the noise has been too complex. That depending on how you tune it, you either find some very known kind of transients, which is not interesting, or you just find various kind of noise that overwhelms your system. So it's kind of none of those approaches seems to be ideal, at least with the techniques we have now. I think the current best idea or approach is to have basically many parallel selves, so that you have a range of different models tweaked for different science goals that are running in parallel, including some that are maybe just random, or some that are just looking for individual objects that have, or individual features that are extreme in one way or another, and then having these run in parallel, and then seeing what we get. But it is one of the outstanding questions: will we be able to find these unknowns that we know are out there? I just think the based on the data that we're getting, you still need to have some system for how to deal with it. There is no The kind of the idea that we can kind of tune down the alert flow until we get a data rate that we can look at obviously doesn't solve the problem. That's
Yeah. I mean, yeah, in AI we throw in this kind of like these definitions like supervised learning, unsupervised, of which anomaly detection is one of the branches, which for me I like fundamentally, the complexity of those are fundamentally different. Like supervised learning is very well defined, and even what we call now semi-supervised, what is a language model. We know what we want to predict in the data, and so it's just a function that we want to learn, and we want it to generalize. But anomaly detection has always been something very complicated, because you always have to explain what is normal, and that's more or less doable. But compared to that, what is not normal, that's like it goes everywhere in the space. So it's really, really hard, and that's probably very hard for living systems too. But we have a very, evolutionarily we were built to do that. Otherwise we would have died. And so I don't know if there is any analogy for this in this, but because these things will not die if they make a mistake. We just lose maybe some knowledge that we could have gathered if we tuned the anomaly detector nicely. But yeah, it's still, this analogy for me, this building this giant brain on top of this perceptive input that comes from the big universe, that amazes me.
Yeah, it is amazing. I mean, I think the coming decade, the coming 2 decades or something, will be the combination of. So it's not just LSST. There will be a range of new observatories with these different messengers that I hope will be constructed, and it's kind of the combination of these with the new AI techniques that, in principle, it will allow us to discover just completely new facets of the universe that we had no idea existed before. So this is this scientific kind of potential here is extremely exciting. It's then the question how we can go there in a way that doesn't drive everyone insane that's trying to do it. And then, of course, how to avoid missing these obvious unknowns. I don't think we have a clear solution for that.
Yeah, I have another interesting analogy, which is if we go to business, like language models, where you know that you can make a product that will make money, you can allocate a lot of money to actually build it top down, a lot of engineering. If you look at like the latest one is Gemini's white paper, which has, 500 authors, and it's a tightly organized hierarchical organization that built it, which is quite new in computer science, by the way. We usually work in smaller groups. But something which we don't have this luxury in science, because let's say value is not so tied to money, or we don't, like the number of people working in this domain is always less than the amount of job that has to be done. So there is always this scarcity of workforce, attention, money, people, which forces you to invent interesting mechanisms or interesting organizations to deal with it. And that was one of the other things that I really found interesting, that LSST doesn't have the resources to deal with the alerts, and doesn't have the resource, for example, to build a database which is fed real time and which can be queried real time, because there would be too many people trying to query. And so you came up with an ingenious structure where you have what you call these brokers between the raw data and the people who are interested in it. So explain me a little bit that organization.
Yeah, again, we get back to these 10 million detections that are distributed every night. Most of them will not be interesting, but a subset will be interesting, and there's no way to predict which events will be interesting, when that will happen, and how many would want to access that data. It's also impossible to predict how much data people would request to find these interesting transients. So hence the idea that these new detections will not be accessible through database, but through alerts that are distributed. So single things saying, I saw something new. And the way these are distributed is through a network of brokers. So from LSST, there will be streams of alert going to a fixed set of endpoints, brokers, and they will then be responsible to distribute this information further.
And so these brokers belong to separate organizations?
Yes. Mm-hmm. So they are basically the LST organization then funds the bandwidth out, but then the different brokers kind of have to develop their own funding structure and their own funding scheme. And as you know, in science, that's always a challenge. It's a but anyway, at the same time as it's a challenge, it's also an opportunity, because it is in a field where dealing the science of opportunities of these data streams is of course extremely large. And I'm sure we'll get more into machine learning. It's also kind of the prime area to apply machine learning models to data streams. So it's a very attractive place to be for people interested in developing machine learning models for astronomy and real-time astronomy in particular. So I think that in itself motivated the creation of a lot of these broker infrastructures.
So what are their incentives?
The incentives, I think there is, that's a good question. I think the incentives are slightly differ between the different teams. I think one incentive, as in a lot of science, is that this is something that you can get funding for. Basically, you can go to a funding agency and saying, this is important. We can distribute these alerts to this community of scientists, and this will allow us to do science, and this is an opportunity to attract funding. But it's also, of course, the science potential that I think a lot of the teams interested in doing this are also interested in doing science and learning how to deal with these data streams. And of course, science in itself provides an incentive for people that actually enter this game. So I think it differs, that the kind of, partially it was kind of a piece of the funding infrastructure that was left blank, and partially it's a very fertile ground for actually doing science. It's
and from a methodological point of view, it's interesting because it's distributed, and so you have space for independent development. When it's top down, if you know what you're doing, it's good, but if you're searching, then the randomness of distributedness helps.
Yeah, and it's something that we have seen in that the different broker endpoints, I think, started from different starting point and has actually developed solutions with their very different focus. And that are, I think, in the end will be good for different science applications. At least that's how I hope this will work out. So people, these things started from different science group interests, and that has then motivated what they developed. And I think we're all surprised in kind of the breadth of the different ideas that came out of this.
Okay, so let's talk about AI a little bit, because it's for sure there's a lot of work in actually just coding the pipelines and maybe rule-based detectors in these pipelines. But obviously one of the candidate technology to try, since the incoming things are images, we have these beautiful image recognition solutions for now.
Yeah.
Why not use AI for this? So what is the status of AI, and how do you see its advantage and disadvantages in these pipelines?
So this is in terms of a pure image analysis, I would say that this is an area where AI has gotten very mature. So it's kind of, and I think it's one of the first stages where it become established practice in astronomy, and that's as this first layer, as you're saying, we can do very good image production, and particularly recognize whether a transient, whether one of these detections looks to be real, or whether it is some sort of image artifact. So that is by now already taken for granted. There are still people who are skeptical to AI technologies, but they don't realize that we are already assuming that this is happening. And in fact, this number of transients that are being distributed, that's after this layer. So it has already gone through a first image analysis layer, specifically designed to detect kind of irregular or non-real looking transients. So if that layer wouldn't be there, then the number of detections would be even larger. And that's so that's something that we're using very successfully with kind of a precursor called the Zwicky Transient Facility that's running now. And it's what we're assuming will be in place for LSST. And it's scheduled, but it's one of those things. Maybe it doesn't work. So we are already in a stage where we are building an experiment, assuming that at least it will be built on some AI model, and it's not even discussed or questioned. It's just a computational necessity.
Technology, yeah.
Yeah, and at some point, very early on, people were skeptical, but not anymore. But then we come to later stages in the pipeline where you get, the next stage will be to classify these things, to figure out, and we talked about the different kinds of transients, and that's a hierarchy that you can go down to arbitrarily specific kind of subclasses of
yeah,
everything.
like the end there is the individual object, right?
Yes, exactly, and they're all unique and exciting. And this is a very active area right now, where different technologies are being tried. Some are based on features, some are really looking at the images, and where we are trying to see how far can we push these technologies in terms of distinguishing the different kinds of transients. So again, I think a lot of the LSST science era or the assumptions are built on the idea that this will work. This is how we will have to deal with these transient data streams. And the only question is, how good can we make those models? And for which science purposes will they be good enough? And there, I think the question is very much in the open. There is kind of a range between more realistic models, maybe more modest, that are running now and trying to focus on actually getting something that works, and then kind of brand new kind of model developments that are very hypothetical in its stage, but might not actually work when applied to real data.
So where do you get the training data for any of these tasks? Because that's always crucial. Do you have labeled real versus noise, or categorized data from earlier experiments maybe, or how does it work?
So it's a you never have enough training data. You never have the training data that you actually need to do the classifier that you need to have. There are different approaches to this. There are unsupervised methods. So far, they haven't behaved, or they haven't performed very well. Maybe they will, I don't know. Then there are very supervised models that have taken different approaches on training data. Some are using labeled, confirmed objects from either other surveys or from the same, like subsets from the same survey. And this is Of course, you have the usual problematic. These samples are small. They are usually biased in terms of the features. There are, of course, methods you can try to correct for that. Again, we don't know how well they will work. Other approaches has been to simulate transients, right? I mean, there are, for a large fraction of different kinds of these objects, we have models for how they could look. We can take a model for how the observatory should work, and we can try to simulate data. Again, and then train our classifiers based on those. And this is kind of, for a lot of the current experiment, this has been the go-to method because it actually works.
Yeah.
You have a bunch of models, you can simulate them, you can train something, you can simulate a new batch of data, you can test your model, you can say this is working amazingly.
Yeah, that's amazing. I mean, you know, the self-driving car pipeline also has that, and perception also has that. It's almost like what I was talking about, like we project our model and detect the differences.
Because so this is something we have tried with CTF. When we try these models on real data, they don't work, at least so far. I mean, I mean, to some extent they work, but not at all like as well as with whatever simulated data set you can have. Again, we don't quite understand the variability that's out there. We don't understand the noise of our own detectors and the universe because it's complex. I think the methods that at least our group find most promising now is to take the small labeled real data set we have and augment that to cover wider parameter ranges. So this is something we're trying right now, but I think the jury about all of these methods is still out.
And it's crucial because this will make us miss, right?
It is crucial, and I think one of the aspects that's not being discussed is that we will not create a perfect model, and especially not at the first trial. And the only way to figure it out is to test our model. And in the end, that will be our only way to evaluate how well that works.
On the real observations that we
on the real observation.
So, but how will you know if you throw away those that are not detected?
Yeah, I mean, this is well, you would have to do some smart sampling of the data, right? You will
keep some of those that are not detected, so you get an unbiased estimate of the
exactly. From kind of a, I don't know, theoretical point of view, we have those models. We're proposing to do these tests, but we run into another almost sociological problem here, and it almost goes back to this proactive reactive way of doing science, in that in order to confirm our models, we need to use quite a lot of telescope time. Again, you mentioned before that for most telescopes, they're not a survey, but rather you have some body that controls the telescope, you propose to use it for some task, and then they rank proposal, and if you're lucky and if you have a good proposal, you get some time to use the telescope for your goals. The problem right now is that kind of where proposals we are writing is that we have this classifier with 90% probability. It predicts that this observation is noise and non-interesting. Can I use your fancy telescope to observe, to confirm that I'm correct in saying that this is just uninteresting? And of course, this goes again, this complete grain of this kind of reactive way of looking at first finding something and then following it up. So usually that goes against this whole system, and partially for good reason. If you have someone that proposes, I have this exciting supernova that I want to observe, and then you have someone else saying, I have this noisy star that I think is uninteresting, I want to observe it, and then obviously you're going to give the time. So that will require a sociological shift where a lot of our resources are actually spent confirming or falsifying our main models that we use to draw our scientific conclusions. And I don't know, I'm sure there are analogies to greater usage of AI and how it plays out in society, but that's definitely an aspect that we will need to figure out during LSST, for example.
No, I mean, the analogy I have is wilder.
Yeah.
When you meditate, you know, that one of the metaphors that people use is that usually when you function, all your senses are transparent to you as the conscious central agency. You are not really aware of how your eyes work or how your touch works. You just touch and feel. But sometimes they go wrong, so you have to calibrate them. That's one view of meditation, where you actually take off the glass and look at it and clean it and put it back. So it's almost like that. You will need to dedicate some meditation time for your LSST telescope, where it actually looks at itself and tries to make, self-deception is what it's called for us. So I don't know, it's like a sort of deceptive observables where you observe your own noises and you think you found something interesting, and that's sort of madness.
I was thinking of the very untasty analogy of self-driving cars, where maybe we need to calibrate them by killing a number of people when it goes wrong as some sort of price to pay to actually getting to work. And then it's a question, so when is that actually worth it? If you compare with long-term other traffic deaths, that's another kind of question that's not really nice to ask or discuss.
Yeah, probably not with this example. Yeah.
No, I mean, it is.
But it's definitely, absolutely. I mean, that's the trade-off of every living organism. That's why we explore. That's actually, we'll get there why you're an astrophysicist, but it's somehow the drive to know more, even if it takes risk for a mammal that exists. Like the dog goes behind every tree to sniff what's there, even though there may be a lion there, because the risk of figuring out if there is some food there or something he can use, worth it. And so we even like the default, if we are not in a state of fear or anger or some kind of like heightened state of affect, we are almost automatically go into exploration. So
and that's of course always been the idea. We see science as and basic science as kind of the ultimate expression of that drive. But and with the new AI development, I mean, I sometimes then ask myself, and I guess we'll talk more about science in general later, is that really the case? Are we really interested in exploring, or are we really only interested in getting food and shelter? Did we look up into the stars to actually find out what they are, or did we look up just to ensure that there was no wrathful God striking me right now, and to kind of ease my fear? I don't know.
But I mean, those are very deep questions. I mean, I have some ideas around it, but for sure, I mean, that there's the basic individual drive of exploration, but there is somehow this sociological drive of exploring as a group, and this is what now science is. We are not the lonely scientist we used to be, or the lonely person who looks at the sky and tries to understand the stars, but we are part of organizations who do it at a much finer scale with sensors that individually we don't have. So that's what it reminds me. So yeah, let's talk about science, and especially like how you became a scientist and why astronomy, why astrophysics, why not something else? Because those are the questions that we can maybe answer on the individual level. And that was the question also I asked in my presentation, and it turned out like, concretely I asked like, why are you guys doing astrophysics? I usually ask that question for a very concrete reason is because I was the director of the Center for Data Science in Suckley, where we had to make decisions on basically like a funding agency a little bit, but of course I was more like a scientist. And I realized that I have no scientific training on how to decide between looking at Mars craters or looking at a hospital pipeline or looking at behavioral economy. How do I decide where I apply my AI expertise? And so it was a regular question we asked to the people who came to us for help, for allocating our attention to their problem, to explain us why their problem is important. And so this is why I sometimes ask it in my presentations, because I'm really, really curious. So tell me, why are you an astrophysicist?
Okay, let's start there. I wish there was a story like that your father, that he built telescope as a kid, or that my father had when I looked into the star and I always wanted to look at them. But there is no such story.
So your father did?
No, he didn't.
No, he didn't. Okay.
No, I mean, he is very scientific, but in other directions. No, I had no original motivation to get into astrophysics. I think I wanted to do something exciting and new, and doing something in science seemed like the way to do that. I think that conclusion might very well be very different today. I mean, we have with the development now, there's certainly not only discoveries being made in the universities, but that's a different. That was the feeling I had at that time, and then it ended up being astronomy and astrophysics. That was just a coincidence. I started doing philosophy and math, but I felt that was too abstract, in the sense that it did not feel like it actually, in some sense, that it was very beautiful, but it didn't mean anything to me in some sense. It was not concrete enough. And then there was a path from there that was mainly driven by randomly meeting people that were interesting, or that had job offers, and interesting sounding projects, and kind of then it was a random path until where I am now. So that's the I think that's the explanation, and I think there is no, in some sense, deep connection to astrophysics in that I'm thinking this is the most exciting thing one can do. There are many things I would love to be able to spend my time doing, but it is exciting, and I'm for whatever small fraction of my time I actually managed to do science. It's very exciting, and I think my only wish is that I would actually have a larger fraction of that time to actually be able to do more astrophysics.
Because what do you spend your time on?
I think this is I've discussed how amazing the science potentials are for real-time astronomy. At the same time, kind of the work climate in academic institutions is not that accommodating. Basically, and this is probably something that you've discussed before, that being a scientist means that you are a scientist, but you're also a teacher, you're a project manager, you're a politician, you're a supervisor, you're a cleaner, you're a writer, and all of these kind of roles have to be somehow stitched together, and you have to find a way to manage them so that you fulfill all your duties, such that you are kind to people and still manage to find some time to actually fulfill these science questions.
I see. Okay, I understand. Of course, yeah. I thought you would talk about technical stuff like coding and
yes,
writing
I mean,
the pipelines. I don't know. So what is your group doing, and what are you doing?
So that's part of it. In some sense, right now, the coding and this working out this infrastructure almost feels like scientific work, and that is actually contributing to that. But yes, that was maybe what I folded under project management, in the sense of trying to get this ample, this framework that we're building, and keeping all the pieces together and make sure it's developing, which is a different task. So
and where you say project management, so you have people that you direct?
Yes and no. There are people that are working with me and that you try to coordinate with. It's not like in a how I imagine a larger company where there are people that I can direct to do this or that. It's like everyone in the academia, you're doing things that because you want to do them, right?
Yeah, I mean, in R&D in larger companies, it's not very different. They have a little bit of more leverage, but it's very much about persuasion and convincing people that what you want them to do is interesting for them for one reason or another.
Yeah, and then trying to direct everyone's energy so that you have a common goal, and that you make sure that the most critical things are done first. Yeah. And that you kind of try to do that as well as possible.
Yeah, I mean, it's fascinating how you have these different levels in the collaboration. We talked about like the highest one where we go, and then you have your individual level, and then between you have all this like tissue of small group energy, behavior, and incentives. And how it works at the end, it's sometimes a mystery.
It is, and this is. And this is, of course, a very evolving picture. These different groups, again, getting back to this organic ID, and the question of what's the optimal size of those? How do they interact? What do you do when they're growing? Can they still be small? I mean, there are a lot of questions like that that are kind of, I guess, evolving now, where I don't know quite where it will end.
Yes, exactly. The right word is evolving, because in like a private industry, I saw more of this expertise consciously being used, like organizational expertise and reorganizational, like coaching and external people who come in and look at your organization and try to modify it with hard work, because it's always hard to do something organizationally. But I've never seen it in science. It's sort of more like it's more based on the individual motivations and incentives that somehow work out on the group level. But I think like when we go into physics, especially when these bigger experiments evolve, they start to work like industrial organization, because they have to, right? You have to build stuff.
Yeah, when you get to that large scale, you have to have at least some consideration about that. But I think in general, just I don't know if it's driven by the culture of science or the funding scheme, but I think one of the major problems is that these sort of tasks are very much needed, but they are very rarely appreciated. I think, as you say, I mean, it's obvious that you need these sort of to have good project managers would be amazing for a lot of projects. It would especially make them last much longer, create an impact. But there's just no space in that, as long as it's kind of this idea that we are living as creative science islands that are, again, looking up at the sky and thinking about what could be the explanation for this. So it's kind of another sort of mismatch there.
Yeah, and some of the private companies, especially for example DeepMind, but I also even know Meta, like Facebook, they do dive into not only AI but using AI for sciences, and it's an interesting. A lot of things came out from DeepMind, like protein folding, or I don't know if they are in the space of astrophysics too, but on biology they are pretty present. How good those tools are, of course, it will be decided by maybe more professional science teams, but there's definitely a lot of buzz and very interesting how AI can be used for all these tasks that we have trying to solve. So maybe there's definitely with the AI boom, there's more interaction between those two worlds.
Yeah, and of course there is it's at least a possibility that the AI tools will be able to make a lot of what we're doing more efficient, like software writing, which usually scientists are crappy at, and maybe we will learn to use language models to do that much better and to integrate the tools that we're developing, just so that it can allow people to actually spend more time working with scientific problems. I think that's something that's definitely happening now, and how well it will work in the end, I don't know. It's
I'm also very curious about this. We even have like projects now going into that direction because everybody's excited by that. I actually joked, like, I don't know, maybe 10 years ago when data science became a thing, that paradoxically data science will be the first one eliminated because we are data scientists. We want to make our job easier, so we'll eliminate ourselves, and that's actually maybe happening. It's amazing.
Yeah, but how far do you think that can be taken? I mean, that's
I don't know. I tell you in a year where we end up, but it's definitely a project we are looking at now.
Yeah.
I mean, it's experimental. For me, data science is completely experimental. Actually, I learned a lot from you guys in experimental physics about how to do experimental science, which is not what computer science used to be. So we have a lot to learn, and so it's experimental science, which means we have to do experiments. I cannot. It's very few things you can actually derive top down from theory in AI. It's actually a doing thing now, which is similar to, I don't know, experimental physics.
That's interesting that you're saying that, because in the past years, I mean, we have had various collaborations with computer science groups, and it's been very interesting. We've learned a lot, but in the end, we often encounter this, I wouldn't call it culture crash, but the methodology crash, where I think, as I also mentioned before, most of their groups were very small, and they were isolated, and they were kind of working on one isolated theoretical computer science problem, how to derive the perfect database query or something like this. And it never actually matched the needs we had. We're typically drenched with data right now, and we just need a database that works. And yeah, maybe there is, the AI is kind of the interface that will make all of this kind of fold together.
And also industry, because most of those things are sold in industry. I mean, computer science research was always sort of like going into that direction because that was its role. It was research. The practical things are usually solved in companies. But I remember, like, when I started working with physicists in 2006, the grid was being built for the LHC on technology that didn't exist. So physicists, smart people, a lot of smart people, and a lot of them went into this direction of building the computational grid, the distributed thing. Of course, also because it wasn't top down, you didn't have one institution that could finance the whole thing. So they had to invent a lot of technology that supported the distributedness. So it's one of the drives, actually. I mean, big physics is a technological drive, like the magnets that we did in the LHC are something that we use now in the MRIs. So this interaction.
It's very curious whether that trend continues, whether there can be some reversal. So we're actually now even more directly applying models from the commercial world, or whether there is this middle ground where, I mean, we talked a little bit about these biological kind of cells and entities and how they interact, and that's one of the kind of and to some extent it's related to the grid, in that in some sense it's distributed. You could view it as some sort of distributed models, and it is one question whether in some sense, both scientific theories and sensors can live as such distributed models and learn to interact themselves, and that's maybe the kind of a in an ideal world that could be a new kind of the grid that might be born of how we have to deal with these data streams from our different observatories.
Yes, I know, I see what you mean. The thing is, like, even in AI research, it's usually research, we're working on algorithms, and we see the top of the iceberg, which is, let's say, OpenAI or Google or Facebook, who in this very narrow domain, which is language models, manage to build research and very fast build it into products. But if you go down in this iceberg, a lot of companies are struggling with how to make machine learning models robust and productionalize them, and the infrastructure around, because it's so random. There is statistics, it's not like a software where you can test exact behavior. It's a lot of struggle. I mean, perhaps the biggest domain where it is happening is the self-driving car, of course, because there's a lot of market possibility there, but you see how slow it goes. A lot of companies are closing, and Tesla is struggling with the full self-driving for reasons that are hard, because they are, they work in the real world, and once you start putting the data science into your pipeline, or AI models, it is interacting with the real world. It's getting the data, otherwise you wouldn't use it. And so these things are not they exist in big companies as they exist in like scientific pipelines, and I think because you guys are smart, you can actually innovate on that front, how to make automatic AI pipeline. Paradoxically, it's not easy.
I mean, it is interesting that you say that also these kind of models are struggling when they're kind of exposed to reality. And maybe one way that also ChatGPT, maybe it actually hasn't really been exposed to reality yet, because it's seen through our filter where we are amazed by it, and it hasn't really maybe we've talked so much or in the community what the impact it had, but maybe it doesn't actually have the impact that we assign to it yet. and I mean, going back to the models that we are using, that a lot of cases, the simplest models work the best. So not using the most advanced things, but just simple model, but that have actually been trained on real noise and knows about real noise, typically perform better than the most fancy newly developed things. That's the...
Yes. I mean, of course, everybody in the industry knows this. Most of the models are XGBoost.
Yeah.
It's robust, it's beautiful, it works. It doesn't know how to generalize out of data distribution, but neural nets are not particularly good at that either. And at certain complexity, where you have this sort of feature spaces which we have in text or vision, they are not as good, because they are, let's say, simpler in sort of the representation capacity that they have. But for simple tasks, yes, it's a very interesting time to live in, and a very interesting domain to study from this point of view too. Like, the research is, and especially because of the great success of computer vision and language models, people tend to, all the conferences are now about deep learning, whereas most of the industry applications are on tabular data and XGBoost. So it's another interesting discrepancy, and I like very much that the smaller data domain, where we have still a lot of interesting things to do. But because of how it works, the buzz is on deep learning now. Yeah. So, but I mean, it's fun, and especially we are on the user end of language models mostly, because there are very few, players in this field that can really train those competitive models. It takes like 500 million to $1 billion just to train a big language model today. So, and as a user, it's a very interesting space. I'm a big fan of GPT-4 for various reasons, for various uses. Writing is one of them, which is obviously one of the main uses, and I will have some guests talking about this because I'm very much interested in how people actually use it. And coding is the other. So you're right to say that it's an exciting space. I mean, be careful with it because it's it can give you a lot of things that read people have already done, but you don't know. But if you want to do something that nobody ever coded, it's tricky.
No, it's a I mean, that's a question that we've had and that we experience in a lot of projects. For specific coding questions, how do you get something that does this? It has worked fantastic. But in terms of scientific writing, so far, sure, you can write things in that mode, but it's never, in what I've seen, never actually good, in the sense that the whole idea of writing a scientific text, when it's actually good, is to write something where basically every word logically motivates the next, and you're saying something new. And actually, the best scientific writers are the ones that can compress their thinking into kind of the shortest amount of words that express their new logical conclusion in a way that makes sense and in a way that's new. But typically, what we get, at least from these versions from ChatGPT, does not work like that. Again, I'm not able to write scientific text in that way. I mean, it's really for the experts. So maybe it's an unreasonable claim. But I think this is it kind of goes back to this challenge that the whole idea of scientific writing is to write something that is new. You want to write a conclusion that's new, and the whole idea of a generative model is to produce something that someone wrote before. So
it's trickier than that, but yeah. I mean, hallucination is about when it invents stuff, so it does invent stuff. But yeah,
it does invent stuff. But how do you how do you tell it to invent the right thing without actually having done it?
Yeah, that's true. That's true. So yeah, so I think it's the use case for GPT and all language models is still out there. So I mean, the jury is out there. We don't really know. I usually use it to post-process and make my writing smoother, or ask for finding an example of some kind of abstraction that I wrote, so to bring it closer to somebody who wants more concrete stuff. So very specific things, and not to actually write the whole article. And I think a lot of people are using them in this sense. Like, you can also summarize research with it, because that's just things that were out there and you just want to have a short.
That is actually very impressive. It would be nice for someone to do some academic study and actually verify how good the summaries are. I mean, they always look very good, right? So
yeah, that's true. Yeah. In any case, I mean, yeah. So it's a limited use, and I'm always, like, smiling at people who think that we are at AGI and this kind of algorithms will wake up and do something nasty, because they just, information processing tools, but pretty intelligent ones. Okay. So is there anything else that we haven't covered that you'd like to talk about?
I don't know. I think it's for before we started talking, I was kind of uncertain what we would have to talk about, since I'm not working with the solar consciousness, and I'm not a computer science AI modeler. but rather as by necessity to fulfill the task. It's kind of tools you have to grab to without knowing and not as much as you should. So I thought the conversation was very nice for me. I don't know if I have anything more to add. I think it was very interesting.
Sounds good, and thank you. No, it's. I mean, I'm interested in a lot of things. That's why I was the director of the Data Science Center for Data Science, because I could get to work with a lot of different things, and that's, it's my nature, and that's why I'm actually very interested in how you choose, because there are a lot of interesting things to do. Yeah.
Well, I mean, I think about choosing. There is no you're just the boss. You choose. So do I get the money?
Say it again.
So do I get the money?
Which money?
Oh,
I didn't get the start of the joke. Sorry.
So you're going back to your hypothetical institute director. Would you give the money to to real-time astronomy?
It's never an absolute decision. So that's what I learned. It depends who the others are, but it's definitely something I would be very excited to work on, and definitely, I mean, we would have to be more concrete too, what you get what you want the money and the AI expertise for, and we try to design even like a software system around the idea that what we are good at, we are not good at productionalizing AI code, or we can do also research, but it's probably not for the kind of projects that we funded, because we wanted something more compact and short. So what we were looking for is do you have all the ingredients for me as a machine learning expert to actually do something useful? So one thing was, you had to explain how excited you are and what the science is, but usually people pass that one. And then the next questions were, do you have the training data? Do you have the labels? Do you know exactly what you want to predict? Can you measure the error? And is it, does it have any research spice on top of it, or is it just a standard problem? If it's standard, we can just try to data challenge and give it to students, or we have to work on maybe because it's out of distribution or something like that. So these were the interestingness features that we looked at. So I had a postdoc who worked on Euclid, which is very similar to, it's another telescope. I think it's a space one, but they started to work on already AI in the detection pipeline. So I knew this a little bit, but of course not as profoundly as you. But it's definitely, it would have been high on the list to fund. Yeah, so you got your money. Okay, so thank you very much. So I usually ask my guests to ask me one question at the end.
Right. Okay, so here's one thing. I a little bit have the feeling that most of what I said kind of confirmed things you already thought, or I had said, or that you kind of suspected. And consequently, you can think of, so now we're doing a podcast. We're having, I think, a discussion that we all find nice and interesting, but will it actually change anything in what we do in terms of practical? And if not, I mean, you must have a reason for why you're doing this podcast. And can you think of a guest that would actually present something, an argument or usage that would actually change what you're doing in your life? That would say, yes, I will from now argue against AI. I will stop my work and become a monk. I will become a politician. What would the guest that actually can challenge everything you know and think as a rationality behind this?
Thank you very much. I haven't expected this question, but let's say I have. I don't think convincing works. I think
Because we already.
debates are overrated. The format. What works for me and why I'm doing the podcast is more connection. So the person or the conversation that could change me would be somebody I would like to become. And I think so that's behind any connection. And somehow, I got attracted to you, not like, in a as an intellectual way when we talked for some reason, because I found that what you were working on and what you were talking about was somehow connecting to my thoughts or me as a person, and we had a very nice conversation in this reception area, which was a little bit noisy and everything, but it was still very nice. So I don't know. So these things work in a very subtle way. So I cannot give you, because it would be very like left hemisphere that, okay, you said something and that changed my mind and now I will do this. What I see more is like a dance where we converse, we get to know each other, we get to know what excites us. I see your emotions and I get excited when you get excited, and that sort of like slowly maybe transforms me into a direction. I definitely know now more about the problems of astrophysics or LSST or the organization around, and also the technical problem. In that sense, I get out of this conversation enriched, but I could not really pinpoint. Okay, from tomorrow on, I will do this differently. It will probably add something to who I am and what I'm looking for. And actually, this podcast has been really interesting, this point of view, because you said, and not only you, like a lot of people who I ask, how did you end up astrophysicist or physicist or economist? There's a lot of luck in that. Like I talked to that people, and that was exactly this process. Like you talk to them, and then somehow they got attracted through them to the subject. And so this podcast is like there's a lot of randomness in it, because I don't have like a fixed guest list that I want to. There are people I am contacting and that I want to talk to, but there are a lot of serendipity in this. Like I have some Twitter conversations with someone, and for some reason I want to talk to them, and that conversation will that change me. So there is this process of change, and maybe it accumulates, and in a certain moment I do something big that's very visible. But I think the effect that these conversations have on me are more subtle and small, and they change me, but not in a drastic way. So I don't know if that answers your question, but yeah, what do you think?
No, I think it does. I mean, I guess I guess I had two thoughts in my head. One was this general one that we often talk to people that we are pretty similar to, and that's the question: is that then is that reinforcing our what we already kind of subconsciously or consciously believe, or does it really expose us to new ideas? And the other one was more directly related to AI, and there the question is, I mean, it's not so much what these AI models can do and how they look, but rather when they get the influence to change how we are acting, what we actually do.
I see.
That wasn't the
So
question
yeah,
I asked, but it was.
I mean, but both are very interesting. So the first one is I did talk to people I didn't agree with. Like Bogdan was an early guest who was a student of mine, and I knew he went into the direction of maybe more pessimistic on AI and more cautious. But my approach is not really to argue or to even collide things in it. It was more about understanding him, where he's coming from and understand why he is where he is. And somehow, I mean, that's my goal with this podcast. Is not about. There are a lot of those debates out there. If you like them, you know, they somehow get a lot of hits too, because people sort of like identify with one of the persons and get this like hit out of it, that what you were just saying, that like reinforcing them in their own identity. But what I'm looking for is more like understanding, like there is this notion of stillmanning the other, and it's usually in the context of making your argument stronger by not arguing a straw man of the opposition, but the stillman, like the best possible case for the other. And what I find is actually that the stillmanning process is itself more interesting than than arguing, you know.
Yeah.
And it does change, you know, what I think, and I can identify with Bogdan. Then, you know, I see it enriches my point of view. It will not it might sharpen what I think. That's not what he thinks, but it may also make me softer and accept his point of view. And this is happening. And the other one on AI, remind me.
So this was not a, I don't know if it's a,
how does it change us, right?
Yeah, and how I mean, this general question, which I think is actually more interesting than how advanced ChatGPT now is how do we make, based on what do we make decisions, and how do we make sure that we trust information that we use to make our decisions, be whether they come from social media or from ChatGPT or from a scientific model. And I think that in some sense, all of these channels have their information channels have their own drawbacks, but in the end, wherever they're coming from, we have to make a decision. So what information, what propositions do I actually trust enough to guide what I actually do? And sometimes what I think might not matter. It's how I act to other people, and how do I digest these different information channels to actually act and maybe change how I'm acting, or continuing how I'm acting anyway, making a subconscious or unconscious decision.
No, that's an amazing question. So what's missing from AI, and maybe it's even like more profound than just a technical thing that's missing, is what is called epistemic authority. So when I see a proposition or something that has a truth value and I have to decide whether it's true or not, I have two choices. Either I can do the experiment myself because I can touch the table and it's there, and I can look at its color, it's red, or I somehow believe that the person who is giving the proposition is trustful. And so this is what I call epistemic, or it's a term, epistemic authority. So I assign authority to the source of that information. And we developed a lot of tools for that. And the first one is just, you know, personal connection. I can look into your eye and see whether you don't want to deliberately mislead me, or you know, it's not an adversarial situation. So from that point of view, I just sort of like put a check mark here that you really believe what you're saying. But the other interesting tool for that is stories. And there is a hypothesis that actually episodic memory, where we actually store stories, we store concrete events that happened with us, was developed for establishing epistemic authority. So when you ask me about something and I tell you, you can ask me, how do I know? And you'll judge the plausibility of the story I tell to judge the trustfulness of that piece of information. So this typically, like, search engines have that. Like, search engines point to a page, and then you sort of recursively delegate that decision to whoever wrote that piece or whatever is the journal. So all the informational infrastructure around trust is built, like you have the reputable journals or not, or reputable people or not. And so we have this in our mind, not only, you know, a model of the world, but also a model of the trustfulness of the sources. So search engines typically just delegate it to whatever they point to. GPT and the AIs don't. And these are one of the points where they are really bad at. And I'm sure that people who try to make a product of it, not for creativity, which is, I think they are wonderful, but for informational retrieval, they have to fix this. So either it has to come with references, like for a scientific paper or any other thing, or they have to be mixed with search engines if people want to use them for information retrieval. But then you have the risk of they becoming just a search engine. So I don't know if in the space of the complete free creativity or hallucination and search engine there is some kind of product that would have some place, but I'm sure people are looking at it. So yeah, I mean, anybody blindly believing what GPT says is a fool today, because it's not that most of the time it's correct, but if you don't know the information and you just go there and trust it, you don't have any means to verify it other than doing the search. But then it's not it's, you know, it's the search.
Oh, exactly. So, and social media is, of course, even worse, because there you don't even know that you're that you are accessing information with a possible traceable history. In ChatGPT,
I don't know.
Would be skeptical.
Because I think social media is actually one of the infrastructures that we built that, you know, to maintain trust. So I don't know, I go to Twitter, I have people I follow, and I have the history of how trustworthy they are, or how truthful they are, or how reliable what they said they were. So we are almost like running the scientific method there, like it's predicted something that didn't happen, then trust level goes down. So and of course, I'm not talking about the anonymous trolls, but who trusts them, you know, nobody. But for the people who have names and history, it's actually not a bad tool for. It's actually replacing. So it's a funny thing. It's replacing the old structure, the authority, the journal or the journalist.
But that's as long as you are using it the way that you're saying. You're only looking at, you've selected sources that you have given authorization. And in some sense, that reminds me of an old reactive astronomer where this was possible to do. And you kind of subconsciously, you ignored a lot of things, and you said, I'm going to react to this and the sources, and I'm going to ignore everything else. And that's fine, but you're still then limiting your information flow.
Yeah, no, absolutely. No, that's an unsolvable problem, which we all try to manage. And it depends a little bit on how open you are to other opinions, how much you are looking for it, or how much you develop those kind of connections. But one of the things, you know, because Twitter is so ephemeral, so short attention span and connections, that it is hard to go deeper in some of these issues. So that's why I'm doing the podcast, actually. So I thought, like, Twitter is a nice tool for having these very momentary connections, but sometimes I will want to go deeper, and I want to know the person and have a discussion on it, and make myself open to that point of view. But yeah, I mean, this is like the basic dilemma of exploration to the new and the unknown and the scary, or staying within whatever I know and be comfortable with it. Yeah. It's a constant dance between those things.
And it is in terms of these tools that we are developing to deal with LSST data, there it becomes a practical question, because in science we want to have reproducibility. So one of the greatest challenges has been built a system that can handle this data, but where actually in principle you can control for this. So it's a real question that we are trying to at least have some sort of tools to solve.
Yes. Yes, so it's a wonderful way to end. We turn back to LSST. So thank you very much, Jakob. It was a great evening and a great conversation. And these are the ones, these are the kind of conversations I do the podcast for. So thank you very much.
Very good. Thanks for inviting me. I'll look forward to seeing where this goes and all the solutions you'll uncover and the truths.
Okay, thank you, Jakob. Bye.
Bye-bye.